So I want to continue talking about trampolines. Right, so where did this come up with? We had CPS functions, right? These turn all functions into tail calls, which is great if your programming language handles tail call optimization, right? Because then we don't have to worry about the stack growing. But, most languages don't actually have good tail optimization. So we can get around that by building up trampolines. So let's give a little example. So if we have the factorial function, right, we take in a number, and this is going to be our CPS form. So it takes in a continuation, which it's going to pass back of type t, and that'll be t. What do we do? Well, if n is less than or equal to 1, we just want to return k of 1. Otherwise, we want to call fact on n minus 1 with a new continuation, right? K of n times v. So we want to have v, right? Whatever fact returns, and we're going to have k times n, k of n times v. Right, this is our standard CPS form of the factorial function. And what happens? We end up with something that looks like this, right? Fact of 10, first continuation, that calls fact of 9 with k1. That calls a whole bunch of other ones until we get down to fact of 1 with a continuation k10. And that hits the base case, so then we end up calling k10, which then calls k9, which calls k8, all the way down to k0. Right, so this is the whole process of computation when we do it with continuation style passing, right? Instead of each of these passing back up, we have these continuations that sort of match exactly what did fact 10 want us to accomplish, right? That's in K1. So instead of this process, the trampoline sets it up. So the idea here is that we have a trampoline, and it's going to call fact of 10 of k0. And instead of having fact 10 k0 call fact 9 of k1, it's going to pass back what's called a thunk that wraps up this computation. It says, hey, trampoline, I'm done, but why don't you call fact 9 k1 for me? And so then the trampoline will call fact of 9 k1. And this one will return what it wants the trampoline to call for it, right? So instead of having this chain, we just keep on going back and forth. We then go to fact 8, k2, right? That then returns to the trampoline some code that it needs trampoline to run next. And so we end up with a stack depth of essentially 2, right? We have the trampoline here, and then we have the Fibonacci calls right here. And each one finishes, passes down, what do you need to do next, trampoline? The trampoline then calls that next bit of code. And those bits of code, right, the next bit that we want to call are called thunks. I mean, hopefully for, the reason makes sense. As we hit the trampoline, we're hitting a thunk, right? And these are delayed computations. So just like in the CPS transform, we took all of the computations that were left over and wrapped it up into the continuation. This is going maybe one step further, where instead of being a tail call, in fact, we just passed back this call, right? We don't do it ourselves. We pass back that call to the trampoline, and the trampoline makes that call for us. And that prevents the stack from growing. And to wrap this whole idea, this whole computation into a new thing, that new thing is called a thunk. And typically the way that it works is really just defining, right, so if this is the computation that we want to do, then we just sort of write it up into an anonymous function that doesn't take any variables and just runs that computation. So we pass back this whole function that isn't evaluated, and then trampoline calls this function, so then we start doing the computation. And that's really the whole basis of this, right? So you can easily build this into your language or into your own development to make sure that you actually get nice tail call optimization, right? Just by doing this passing back and forth. We'll look at a example in code, but this is sort of an advanced thing, and you're not going to be tested on it, just so you know. But it's a cool thing to sort of see a way to fix this issue. Yeah.